CH1601 video series. For the past couple of videos, we have considered the general reaction scheme for a carbonyl nucleophilic addition reaction. And in this video, we are going to look at several specific examples using different nucleophiles. The first is hydration, where water, H2O, is a nucleophile. The electron-rich oxygen atom adds to the electrophilic carbon atom of the carbonyl group. A tetrahedral intermediate is formed, shown here. Another water molecule will accept this additional proton, which can be transferred to the negatively charged oxygen to form our hydrate product. Essentially, we have moved a proton between the two oxygen atoms in a process mediated by water. If you feel comfortable with this, you can represent this as a shortcut by writing proton transfer, or plus minus H plus. This proton transfer is very rapid and reversible. However, if you struggle with this concept and prefer to draw the full mechanism, then please feel free to do so. You might be wondering why this step here is reversible. The negative charge on the oxygen can push down and kick out the water as a good leaving group. Therefore, the addition of water to the carbonyl group is a reversible process. Interestingly, we find that hydration reactions of carbonyl compounds can be catalyzed by both acid and base. For acid catalysis, the electrophilic carbonyl species becomes more reactive. The H plus from the acid reacts with a lone pair from the oxygen of the carbonyl group. We formally generate a species which is positively charged and has a resonance form drawn here. The carbon atom has a full formal positive charge attached to it, rather than a delta positive charge in an uncatalyzed carbonyl compound. This makes the carbonyl more electrophilic and massively increases the reactivity of the carbon center. In terms of a mechanistic pathway, the water acts as a nucleophile, which attacks the very electrophilic carbon, breaking the carbon-oxygen pi bond and forming a tetrahedral sp3 hybridized species. To yield the final product, an H plus ion is lost. This regenerates the acid catalyst, which is important because, remember, the definition of a catalyst is that it will speed up a reaction, but it will not be consumed by the reaction. Base catalysis, on the other hand, works by increasing the nucleophilicity of the nucleophile. If the hydration reaction is carried out with water and a base, such as sodium hydroxide for example, would the hydroxide ion or the water molecule be a better nucleophile? Of course, the hydroxide ion would be better because it has a formal negative charge and it is more electron rich. So this time, we have increased the reactivity of the nucleophile rather than the electrophile as observed in acid catalysis, and the addition mechanism occurs as shown here. The negatively charged oxygen picks up a proton from a water molecule, yielding the hydrate product and regenerating the hydroxide base catalyst. The next reaction we will look at is the addition of hydrides to a carbonyl compound. If we treat an aldehyde with a hydride, we form a primary alcohol. If we treat a ketone with a hydride, we form a secondary alcohol. In both cases, reduction has taken place. We've gone from having two bonds to a heteroatom in the form of a carbon-oxygen double bond to only having one heteroatom bond. What reagents would we use as a source for hydride ions? Sodium borohydride is a common example. The borohydride has a structure as shown here. By breaking this bond and pushing electron density onto the hydrogen, the H- hydride and neutral BH3 species are generated. So how would we draw this in terms of a mechanism? If we start with an aldehyde and react it with sodium borohydride, typically with an alcohol solvent such as ethanol, we form a primary alcohol. The boron-hydrogen bond is broken to form the hydride, which attacks the electrophilic carbon of the carbonyl group. we form a tetrahedral intermediate, which is protonated by the alcohol solvent to give the final product. You'll notice that this arrow is not reversible. If we were to generate the starting material, we would need a hydride ion to be kicked off the carbon. This never happens because the hydride ion is not itself a good leaving group. Therefore, addition of a hydride ion to the carbonyl group is irreversible. This is what you should consider for any carbonyl-based nucleophilic addition reaction. If the reaction was to be reversible, consider, is the leaving group a good leaving group, or is it unlikely to be kicked out? Lithium aluminium hydride acts in a similar way as a hydride source, but it is far more reactive than sodium borohydride. In fact, it is so reactive that a non-protic solvent such as THF must be used. If a protic solvent was to be used, such as water or ethanol, the lithium aluminium hydride would react directly with the solvent. In this reaction, the first step involves treating the carbonyl compound with lithium aluminium hydride in a THF solvent. We form the tetrahedral intermediate species. In a separate second step, often called a workup step, we carefully protonate the negatively charged oxygen atom. It is important to recognize that the separate steps are represented like this with Roman numerals. There is one more important point regarding the addition of a hydride to a carbonyl. If we were to add a hydride to a ketone, such as this one, with two different substituents, we would actually form a racemic mixture of secondary alcohol products. The hydride can add to the top face of the carbonyl, producing this stereoisomer. But the hydride can also add to the bottom face of the carbonyl, producing the non-superimposable mirror image enantiomer. Why would we not get enantiomer products for addition of hydride to an aldehyde? The primary alcohol has two hydrogen atoms, so there is no stereogenic center in this case, and therefore no stereoisomers. So that's how we add a hydride to a carbonyl. How would we add a carbon-based nucleophile, which we represent as R-? Adding a carbon-based nucleophile to an aldehyde would generate a secondary alcohol, while addition to a ketone would generate a tertiary alcohol. To generate this R- species, organometallic reagents are used, specifically alkyl lithium reagents or alkyl magnesium reagents, which are more commonly known as Grignard reagents. In this reaction, the first step involves treating the carbonyl compound with the organometallic reagent in a dry, inert solvent such as THF. Aprotic THF is used instead of a protic solvent like water or ethanol, which would react directly with the R- group of the organometallic reagent. We form the tetrahedral intermediate species, and in the separate workup step, we carefully protonate the negatively charged oxygen atom. So how would we draw this in terms of a mechanism? Once again, you'll notice that this step is not reversible. The methyl group is a poor leaving group and cannot be kicked off the carbon. Grignard reagents react in an identical manner, using the two-step reaction. For these reactions, the R- nucleophile can also add from the top or bottom face. For aldehyde compounds, if the two R groups are different, a racemic mixture can be formed. This is shown here. For ketone compounds, if the three R groups are different, a racemic mixture can be formed, as illustrated in this example. All of the reactions in this video have occurred through the same mechanism. The electron-rich nucleophile adds to the electron-deficient carbonyl. The intermediate species is then protonated to form the final product. If you follow this pathway, you will succeed in the CH1601 carbonyl mechanisms. Try the quiz to test your knowledge on the reactions discussed in this video.